In this chapter, we are going to deal with the basic CPU scheduling algorithms. We assume four constraints. First, each job runs for the same amount of time, and all jobs arrive at the same time. And all jobs only use the CPU and there's no I/O operations. And runtime of each job is known already. These assumptions are not realistic. We are going to define the metrics for scheduling. First one is turnaround time. Turnaround time is the time difference between when the job first arrived at the system and then when the job completes. So it is computed as completion time minus the arrival time. Another metric is fairness. There are two important attributes to determine the value of the scheduling algorithm. One is the turnaround time, and the second one is fairness. In most cases, fairness and turnaround time conflicts with each other. If you want to achieve performance or turnaround time, you have to sacrifice the fairness. On the other hand, in some cases, if you want to emphasize the fairness of your scheduling algorithm, you may have to give up the turnaround time of your algorithm. The first algorithm you want to deal with is first in, first out. It is also called as a first come, first served. CPU schedules these jobs on the order in which the processes arrive. Assume that A, B, and C arrive in that order, and each job runs for 10 seconds. Then average turnaround time corresponds to 20 seconds. So turnaround time for A is 10. Turnaround time for B is 20. Turnaround time for C is 30. So average turnaround time is 20 seconds. FIFO or FCFS is simple, but it bears some side effect called Convoy effect. In Convoy effect, the process that needs a CPU for a very short amount of time might have to wait for the CPU that consumes lots of CPU time. Let's say A has arrived just before B and C, and A runs for 100 seconds while B and C run for 10 seconds each. In this case, if you look at the timing diagram, turnaround time for A is 100 seconds, but turnaround time for B is 110 seconds, and turnaround time for C is 120 seconds, which sums up to the 110 seconds average turnaround time. To overcome this drawback, there comes a scheduling algorithm called shortest job first. In shortest job first STCF algorithm, it runs the shortest job first. It is non-preemptive scheduler. Non-preemptive means once the process starts to run, the process cannot be suspended unless the process voluntarily relinquish its CPU. So let's say A arrived just before B and B arrived just before C. Okay, and then A and B and C, they are arrived at the system almost at the same time. And then A runs for 100 seconds, B and C runs for 10 seconds each. In this case, in shortest job first algorithm, it examines the runtime of the existing processes and then it selects the process with the shortest runtime. In that case, B and C are executed first, and then A is executed. On the shortest job first algorithm, every turnaround time corresponds to 50 seconds because turnaround time for B is 10 seconds, turnaround time for C is 20 seconds, and turnaround time for A is 120 seconds. At the beginning of this course, I've mentioned that often turnaround time and fairness are at odds. Here, we executed B and C ahead of A, even though we have assumed that A has arrived at the system slightly earlier than B and C, but we execute B and C first, and then execute A. it can be thought as a violation of the fairness because A has arrived ahead of B and C. But in terms of turnaround time, we have saved the turnaround time with a great deal. Now, jobs can arrive at any time instead of arriving at the same time. For example, A arrives at T0 and needs to run for 100 seconds. B and C arrive at T equals 10 and each need to run for 10 seconds. If we apply shortest job first algorithm, then turnaround time for job B is 100, and the turnaround time for job C is 110. So every turnaround time for A, B, and C renders 103.33. Let's add the preemption feature to the CPU scheduling algorithm. So whenever the new jobs arrive, the scheduler is triggered, and then it checks if any newly incoming process has the shortest remaining time or shortest time to run, and selects whatever processes with the shortest execution time whenever the scheduler is executed. We call it shortest time to completion first algorithm, STCF, or we say is a shortest remaining time first algorithm. And time first algorithm, we call it SRTF. Let's review the example. A arrives at T10 and needs to run for 100 seconds. And B and C arrive at T10 and each needs to run for 10 seconds. So B and C has arrived at T equals 10 with execution time of 10 seconds. In that case, A has been executing for 10 seconds, so remaining time of A corresponds to 90. So at this point, execution time of A is 90 and execution time of B and C corresponds to 10. So the CPU scheduler selects B for the execution, and then B is executed for 10 seconds. After B finishes, there are two jobs remaining, A and C. A has execution time of 90 and C has execution time of 10. So scheduler chooses job C and then it executes for 10 seconds. And then finally, B and C completes and there remains only job A, and job A executes for 90 seconds. If you consider turnaround time, then the turnaround time for B is 10 because it arrived here and it gets an execution immediately and runs for 10 seconds. For C, turnaround time is 20 seconds because it has been waiting for 20 seconds to finish. Versus for A, its execution time is 120 because it delayed a lot. So if you consider shortest time to completion first with preemption, then average turnaround time renders 50 seconds. Now, we have considered two metrics. First one is fairness, and second one is turnaround time. Let's examine the third one. Third one is the response time. Response time is a time interval between the time when the job arrives and the time when it is first put into the CPU. Let's say there is CPU and there is a bunch of processes waiting for the CPU to be executed, and a new process TA has arrived at like 11 seconds, and then it gets to the CPU at like 20 seconds. Then in this situation, the response time for TA corresponds to 9 seconds. STCF or related disciplines are not particularly good for response time. So there comes a new algorithm called round-robin scheduling. There is a notion of time slice. Time slice is the amount of CPU time a process can execute consecutively. In the previous example, if there are processes, and then the process has to be executed until it finishes, like there is A, B, and C. But in terms of the response time, they're bad because if the three processes execute for 10 seconds, then B are executed after 10 seconds after it has arrived, and C gets executed after 20 seconds it has executed. So B and C has to wait for a huge amount of interval until it gets executed. So to remedy that problem, we introduced the notion of time slice. So in executing time A, B, C, instead of executing job A until it finishes, the CPU executes A, B, and C in round-robin manner a little bit at a time. It is called round-robin scheduling. The length of a time slice must be multiple of timer interrupt period, and then round-robin is fair, but it performs poorly for turnaround time. For shortest job first, non-preemptible algorithm, the average response time corresponds to 0 for TA, and 5 for TB, and 10 for TC. So average response time corresponds to 15 divided by 3. It corresponds to 5. But in terms of round robin, it is different. For A, it gets executed immediately. For B, it gets executed after 1 second. And C, it gets executed for 2 seconds after. So every response time corresponds to 0 plus 1 plus 2 divided by 3. It corresponds to 1. So in terms of average response time, round robin with time slice of 1 second performs much better than the existing algorithm. However, round robin is not free. Look at the number of context switches. Here, there are three context switches. Let's say this. Here, the context switch has occurred 15 times. Here we have context switch time, 3 context switches. So, round robin algorithm is exposed to a lot more number of context switch than shortest job first does. So if you consider time actually the context switch, then the time of total execution here, if you don't consider the context switch, then all these jobs are completed at 15 seconds. But in reality, the final job, C, gets finished by 15 plus 3 context switches. However, here, the time the job C finishes will be 15 plus 15 context switches, whatever that means is. So if the context switch is large, then the total time between the shortest at first and then the round robin algorithm makes a difference a lot, makes a big difference. The length of time slice is critical. If the time slice is short, then it is better for the response time. But there's going to be more context switches, and then the context switch overhead will be a dominating factor over entire system performance. If we take the longer time slice, then number of context switches gets smaller, and however, the response time is not as good as the case with this shorter time slice. So what is the right length of time slice? Deciding the length of the time slice is determined by the system designer and with an experience. So now let's relax the assumption number 3. So all programs perform an I/O. And let's say that A and B needs 50 milliseconds of CPU time each. And it runs for 10 milliseconds and then issues an I/O request. And then I/O takes 10 milliseconds. And that's for A. And B, it just needs total of 50 milliseconds of CPU, and it does not perform any I/O. Let's assume that scheduler A runs first and B after. Upper half of the figure, you see that this is CPU and this is I/O. So the process A spends 10 milliseconds for CPU and 10 milliseconds for I/O. It alternates between CPU consumption and I/O behavior. Once this is over, B starts to execute for 50 milliseconds. However, if the operating system can allow the process B to use CPU when the A is blocked while waiting for CPU. Then what we can see is we can interleave the execution of B while A is hanging, waiting for this IO completion. So in the earlier case, these two jobs has finished at the time of 140 milliseconds. But if we interleave the execution of A and B, then two jobs finishes a lot earlier than before at 100 milliseconds. So when a job initiates an IO request, the job is blocked waiting for an IO completion. So the scheduler should be able to schedule another job on CPU. When the IO completes, an interrupt is raised, then operating system moves the process from the blocked state to the ready state.